In this video, I'm going to show an example where we calculate the heat transfer area for a single effect evaporator that's being used to concentrate a salt solution. The feed salt solution is 1.5% salt and water, and the exit is 4% salt and water. And the feed rate is given, and the temperature. The evaporator is at 1 bar, and we're using saturated steam at 170 kilopascals to provide the heat for vaporization. And the question is, if we know the heat transfer coefficient, 2500 watts per square meter per degree Kelvin, what is the heat transfer area? And what assumptions do we have to make to do this calculation if this is the only information we have available to us? So the first thing we do in a problem like this is to draw a diagram and define our variables. So here is a diagram, and the single effect evaporator is explained in more detail in another video. Feeding in saturated steam to the evaporator through some sort of heat transfer coil. So the steam leaving is condensed liquid at saturated conditions. Feed is 1.5% and the feed flow rate 7,500 kilograms per hour. One of the assumptions we make is there's no salt in the vapor, which is certainly what we would expect. Some of the other assumptions, one is that the evaporating liquid is well mixed. And so that means the temperature for the vapor, temperature inside, the temperature of liquid, all the same temperature. It also means the concentration, this weight percent leaving, is the same as the weight percent inside our evaporator. The second assumption we're going to make is that the heat of vaporization can be calculated based on the heat of vaporization of water. The fact that it's solution, we can still use the steam tables to get the heat of vaporization. We also assume there's no heat of mixing or unmixing when the salt is added to the water is removed from the salt. This may or may not be a good assumption based on the information we have, not knowing the salt. This is a reasonable first approximation. We're also going to assume that the boiling point temperature increase, namely the fact we add salt, lowers the water fugacity, if you like, and therefore raises the boiling point. We're going to assume for now that that's zero, that the concentration is low on a molar basis, such that we don't get much of a temperature increase. This may not be a good assumption depending on the system, and this can have a significant effect on the heat transfer area because we're looking at the temperature difference between the steam and the temperature TE. Our next step now is to write down mass balances for this system because we need to know the flow rates of the liquid and the vapor leaving in order to calculate the energies. And there's the overall mass balance, the flow coming in, the molar flow rate is leaving as liquid or as vapor. And then there's a balance on the salt. So if we take the mole fraction of the salt in the feed times the molar flow rate, all of the salt appears in the liquid leaving. So this is 7,500 kilograms per hour. And we don't know L, but of course we can solve this to determine L. So this is the total liquid flow rate, which means the vapor flow rate is 7,500 minus 2812. So the vapor flow rate 4688 kilograms per hour. Now that we have the mass balances, the next step is to do energy balance on the stream that we're evaporating. Apply the first law, steady state system, a flow system. There's no accumulation. The energy coming in is the mass flow rate times the enthalpy per kilogram entering the system. And then the energy leaving is the mass flow rate of the vapor times the enthalpy of the vapor per kilogram minus the mass flow rate of the liquid times the enthalpy of the liquid per kilogram. And then the other term that we have is the heat transfer. So it's a heat transfer coefficient times the heat transfer area times the temperature difference, temperature of the steam, saturated steam coming in, saturated liquid leaving, so everything is at water, liquid, and vapor is at TS, minus the temperature in the evaporator. So this is the first law. We can use steam tables to look up values. So what I've listed is flow rate, steam coming in 85 degrees. We'll assume that the 1.5 weight percent solution can be modeled as pure water at 85 degrees C. We'll use the enthalpy of saturated steam at 85 degrees C as a pretty good approximation to the steam at 1 bar in 85 degrees C. Vapor at 1 bar, so 100 degrees C, and then liquid also at 1 bar, 100 degrees C. And then we look up for 170 kilopascals, the saturation temperature is around 115 degrees C. So we can substitute the values for our mass flow rates and our enthalpies into this equation. We're also given the heat transfer coefficient, so our only unknown is the heat transfer area, and that's what we're going to solve for. So let's substitute the numbers in. So here are the values substituted in that we looked up the steam tables and we calculated from the mass balances. Only thing we have to be aware of, a watt is a joule per second. We have to keep units consistent. That's why it's valuable to write units with each of the numbers. So we convert time to hours, convert joules to kilojoules for the heat transfer coefficient. And then the temperature difference in Celsius is the same as the temperature difference in Kelvin. Certainly, 2 significant figures is probably more than we can justify because we made a number of assumptions. And one of the big assumptions that affects things is the fact that the temperature difference here is going to affect the heat transfer area a lot. This temperature is going to be higher for a 4% solution than the temperature difference is less. The heat transfer area would have to be more.